Gold mining, a captivating journey spanning generations, encompasses a variety of methods, each with its distinct tools and techniques. Panning, a traditional approach akin to a dance with nature, involves meticulously separating gold from river sediment, making the toil worthwhile for the prospectors. Progressing from the simplicity of panning, sluicing emerges as a more modern method, enabling miners to efficiently process larger material quantities and enhancing the overall productivity of gold extraction. Open pit mining represents another facet of this adventure, as vast holes are excavated to unearth gold treasures hidden beneath the Earth's surface on a grand scale. Additionally, lode gold mining unfolds as a geological puzzle where miners trace veins of gold embedded in rocks, revealing the precious metal within. Each method, from the timeless panning to the sophisticated techniques of open pit and lode mining, contributes to the rich tapestry of gold mining. It's a journey through time, showcasing the evolution from traditional practices to advanced methods, all driven by the enduring allure of gold. In the pursuit of this coveted metal, prospectors employ diverse methods, each playing a role in the unfolding saga of wealth and discovery. Gold mining involves several methods, each with its techniques and equipment. Here are some common methods of gold mining. Panning is one of the oldest and simplest techniques used by prospectors and miners to extract gold from rivers and streams, where it has accumulated in the form of placer deposits. Here's a detailed explanation of the process. Gold is often associated with quartz veins. If you observe quartz veins in the rocks along a river or stream, it may suggest the possibility of gold nearby. The presence of quartz does not guarantee gold, but it's a common association. Panning is typically carried out in riverbeds or areas where water has washed gold downstream and deposited it in the sediment. Placer deposits are concentrations of minerals, including gold, that have been naturally separated. The primary tool used in panning is a metal pan, usually made of steel or plastic. These pans are shallow and wide, allowing for the easy separation of heavy particles like gold. Miners begin by scooping up a small amount of gravel, sand, and sediment from the riverbed into the pan. This material is likely to contain gold particles along with other heavy minerals. The pan is then submerged in water, and the miner agitates the mixture. The goal is to allow water to wash away lighter materials like sand and gravel, while heavier materials like gold concentrate at the bottom of the pan. By holding the pan at a slight angle and swirling it in a circular motion, the miner uses the natural force of gravity to separate the heavier gold particles from the rest of the material. Gold, being dense, settles to the bottom of the pan. Then the pan is tilted slightly to allow excess water and lighter sediments to spill over the edge. This process is repeated until the majority of the lighter material is washed away, leaving behind the heavier gold particles. After repeated swirling and rinsing, the miner inspects the remaining material in the pan. Any gold that is present will usually be visible at the bottom of the pan. This is the recovered gold concentrate. Once the gold is isolated at the bottom of the pan, it can be carefully collected by using a snuffer bottle or tweezers. This is the final step in the panning process, and the collected gold can then be panned. It is a labor-intensive but effective method, particularly for small-scale or recreational prospecting. While it may not be as efficient as larger-scale mining methods, after the initial panning process, or when starting directly with sluicing, miners gather gravel, sand, and sediment from the riverbed. This material is likely to contain gold particles, similar to what was collected during panning. Miners set up a sluice box, a long narrow channel equipped with riffles, obstructions along the bottom. Sluice boxes are typically made of wood, metal, or plastic, and are designed to allow water to flow through while capturing heavier materials. The sluice box is carefully placed in a strategic location in the river or stream, ensuring a continuous flow of water through the channel. Miners shovel or pour the collected material into the upper end of the sluice box. The water flow carries the material along the channel. Water is introduced into the sluice box, either through a natural flow river or stream, or by artificial means. The flow of water carries the material over the riffles, which are strategically placed obstructions along the bottom of the sluice box. The riffles create turbulence and eddies in the water, allowing heavier gold particles to settle. As the material moves along the sluice box, the riffles capture the heavier gold particles, preventing them from being washed away with the lighter sediments. The principle is based on the fact that gold, being denser, settles faster than other materials. The sluice box is designed to maintain a continuous flow of water. This helps carry away the lighter sediments while leaving the captured gold in the riffles. Inspect the riffles for accumulated gold. The cleanup involves removing the captured gold from the riffles, often using a snuffer bottle or similar tools. The sluicing method is more efficient than panning because it allows for the processing of larger quantities of material in a continuous flow. While panning is effective on a small scale, sluicing is a step up in terms of throughput and efficiency. Miners can repeat the sluicing process in the same location or scale up operations by using larger sluice boxes or multiple sluices to process larger volumes of material. However, panning and sluice boxes are affected to collect a small amount of gold, as opposed to collecting a rich quantity of gold in open pit mining and lode gold mining. Here we discuss how to collect a rich quantity of gold in modern times, but first we investigate the targeted area thoroughly. A series of procedures known as mineral exploration are used to determine whether or not economically valuable minerals are present in a given location. Once targets are found, the process typically starts with extensive exploration over a large area and then narrows down to in-depth examination, typically using drilling and sampling. It is possible to divide the several exploratory phases needed to produce a discovery into stages, and the outcomes of each stage dictate whether or not to move on to the next. For this reason, the exploration process may take several years to finish. The exploration process begins with geologists conducting detailed geological surveys of a specific region or area. During these surveys, geologists systematically examine the Earth's crust, which includes studying the rocks, minerals, and overall geological formations present in the target location. To achieve this, geologists employ a variety of tools and techniques. Geological maps provide an initial understanding of the broader geological context, serving as a guide for further exploration. Satellite imagery offers a comprehensive view of large areas, aiding in the identification of geological features and potential anomalies. Ground-based surveys involve direct fieldwork, where geologists physically investigate rock outcrops, soil compositions, and other surface features. These surveys are instrumental in gathering essential information about the composition and structure of the Earth's crust in the designated area. By integrating data from different sources, geologists can piece together a comprehensive picture of the geological conditions, facilitating the identification of areas with the highest likelihood of containing gold deposits. In the exploration phase of gold mining, geologists focus on analyzing the types of rocks present in a given area, recognizing that certain rock formations are often associated with gold deposits. Gold tends to be found in specific geological contexts, and the types of rocks in an area can provide valuable clues about the potential for gold mineralization. For instance, gold is frequently associated with quartz or iron-rich rocks. Geologists pay meticulous attention to the characteristics and composition of these rocks, examining factors such as texture, mineral content, and structural features. Quartz veins, for example, are commonly linked to gold deposits because gold can precipitate out of hydrothermal fluids and become concentrated within quartz formations. By studying the distinctive traits of these rocks, geologists can gain insights into the geological processes that may have led to the formation of gold deposits in the area, aiding in the identification of prospective zones for further exploration and mining activities. Continuing with the exploration process, in gold mining, soil composition becomes a crucial aspect of investigation. Geologists recognize that gold, which may originate from weathered rocks or mineralized deposits, can manifest in the soil. Soil serves as a repository for the effects of geological processes, including the weathering and breakdown of rocks that may contain gold. In this context, geologists actively collect soil samples from various locations within the target area. These samples become valuable sources of information as geologists analyze them for trace elements and minerals that might signify the presence of gold. The identification of specific elements associated with gold, such as arsenic or iron oxides, can serve as indicators or anomalies in the soil. By interpreting these soil characteristics, geologists gain additional insights into the potential presence and distribution of gold deposits beneath the Earth's surface, contributing to the refinement of exploration targets and the overall understanding of the geological context in the surveyed region. Building upon the earlier exploration methods, the topography of the land emerges as a critical component in understanding the geological history and potential gold mineralization in a given area. Geologists recognize that the surface features, elevation and slope of the land hold significant clues about the underlying geological processes that may have led to the concentration of gold deposits. The examination of the landscape becomes a vital link in the exploration chain, connecting geological features with potential gold-bearing zones. For instance, gold deposits might be concentrated in specific topographical settings where ancient geological processes such as erosion, weathering, or the movement of fluids have acted over time to accumulate and concentrate gold. Geologists leverage this understanding to strategically identify areas with geological features indicative of gold mineralization. By integrating information on rocks, soil composition, and topographical characteristics, geologists can refine their exploration targets, narrowing down regions with a higher likelihood of hosting economically viable gold deposits. The synergy between geological, geochemical, and topographical analysis enhances the precision of the exploration process, guiding subsequent mining activities with a more informed and targeted approach. In contemporary gold exploration, advanced technologies play a pivotal role in enhancing the efficiency and precision of the process. Geologists now frequently employ cutting-edge tools, such as satellite imagery and remote sensing technologies, to gain a comprehensive and high-resolution view of large geographic areas. These technologies offer a broader perspective that aids geologists in identifying potential gold-bearing structures or geological anomalies. Satellite imagery provides detailed visual data of the Earth's surface, allowing geologists to observe large sweeps of land from above. This imagery assists in identifying surface features, geological formations, and alterations that may indicate the presence of gold mineralization. Remote sensing tools, which include various sensors mounted on aircraft or satellites, enable geologists to collect data beyond what is visible to the human eye. These tools can capture information related to mineral composition, vegetation health, and even subtle variations in topography. The integration of satellite imagery and remote sensing data enables geologists to analyze vast regions efficiently, making it possible to identify potential target areas for further exploration. By detecting geological anomalies or patterns associated with gold deposits, these advanced technologies contribute to a more strategic and data-driven approach in the early stages of exploration. This not only accelerates the exploration process, but also allows geologists to focus their efforts on areas with a higher probability of containing economically viable gold deposits. The synergy between traditional fieldwork and state-of-the-art technology is instrumental in maximizing the effectiveness of modern gold exploration efforts. As part of the comprehensive exploration process in gold mining, geologists employ geochemical analyses to gain insights into the concentration of specific elements in both rocks and soil within a target area. This analytical approach is crucial for detecting anomalies and indications of potential gold deposits. Geochemical analyses involve collecting samples of rocks and soil and subjecting them to laboratory testing. Geologists focus on identifying and quantifying the presence of certain elements with a particular emphasis on elements associated with gold mineralization. Elevated levels of specific elements such as gold itself or other elements known to be commonly associated with gold, deposits like arsenic or pyrite, can serve as significant indicators during these analyses. The detection of heightened concentrations of these elements in the geochemical analysis suggests the potential presence of gold deposit in the sampled area. This information aids geologists in refining their understanding of the geological context and in prioritizing specific locations for further exploration activities. By combining geochemical data with other geological information such as rock types, soil composition, and topographical features, geologists can construct a more detailed and accurate model of the subsurface, enhancing their ability to identify areas with a higher likelihood of containing economically viable gold deposits. Geochemical analyses, therefore, form a critical component of the systematic and scientific approach to gold exploration. In certain instances, geologists opt for drilling operations as a more direct and in-depth method of exploration to unravel the mysteries beneath the Earth's surface. During drilling, cylindrical cores are extracted from the subsurface, providing geologists with first-hand information about the underlying geology. This process is particularly valuable for confirming the presence of gold deposits and understanding the characteristics of the rock formations. Drilling operations involve the use of specialized drilling rigs that penetrate the Earth's crust to reach significant depth. As the drill advances, a core barrel collects cylindrical samples of the rock formations encountered along the way. These core samples, essentially geological snapshots from below the surface, offer a wealth of information. Geologists meticulously analyze these samples to discern the rock types, mineral composition, and structural features, providing direct insights into the subsurface geology. By examining core samples, geologists can confirm whether the geological conditions align with expectations for gold mineralization. The presence of visible gold-associated minerals or specific geological features within the core samples can serve as strong indicators of the existence of gold deposits. This direct intangible data obtained through drilling contributes significantly to the overall geological understanding of the area, guiding subsequent exploration efforts and informing decisions about the feasibility of gold mining in the targeted region. In the final stages of the exploration phase in gold mining, geologists embark on a crucial task of integrating and synthesizing all the diverse data acquired during the various stages of exploration. This comprehensive approach involves combining geological, geochemical, and topographical information to create a holistic understanding of the surveyed area. The aim is to identify specific zones or areas with a higher likelihood of hosting economically viable gold deposits. Geologists bring together geological data, which includes insights into rock types, mineral compositions, and structural features. Geochemical data, highlighting concentrations of specific elements associated with gold, and topographical information, detailing the landscape's features, elevations, and slopes. This synthesis forms a multifaceted picture of the geological context, aiding in the identification of potential gold-bearing structures or anomalies. The integration process often includes advanced technology such as Geographic Information System (GIS) tools, which facilitate the overlaying and analysis of diverse datasets. Through this meticulous analysis, geologists can pinpoint areas where geological conditions align favorably for gold mineralization. These identified zones become priority targets for further exploration or development. By examining core samples, geologists can confirm whether the geological conditions align with expectations for gold mineralization. The presence of visible gold, associated minerals, or specific geological features within the core samples serve as strong indicators of the existence of gold deposits. This direct, intangible data obtained through drilling contributes significantly to the overall geological understanding of the area, guiding subsequent exploration efforts and informing decisions about the feasibility of gold mining in the targeted region. In the final stages of the exploration phase in gold mining, geologists embark on a crucial task of integrating and synthesizing all the diverse data acquired during the various stages of exploration. This comprehensive approach involves combining geological, geochemical, and topographical information to create a holistic understanding of the surveyed area. The aim is to identify specific zones or areas with a higher likelihood of hosting economically viable gold deposits. Geologists bring together geological data, which includes insights into rock types, mineral compositions, and structural features. Geochemical data, highlighting concentrations of specific elements associated with gold, and topographical information detailing the landscapes, features, elevations, and slopes. This synthesis forms a multifaceted picture of the geological context, aiding in the identification of potential gold-bearing structures or anomalies. The integration process often includes advanced technologies, such as Geographic Information System (GIS) tools, which facilitate the overlaying and analysis of diverse datasets. Through this meticulous analysis, geologists can pinpoint areas where geological conditions align favorably for gold mineralization. These identified zones become priority targets for further exploration or development. We use a detailed process called lode mining to get a lot of gold. In this process, drilling is super important. First, miners use special drills to make holes in the hard rock. This drilling step is like getting ready before using explosives to break the rock and get the gold out. Miners use specific drilling equipment to make these holes efficiently. They carefully plan where to put these holes based on the mine design and what they know about the rocks. This planning helps when they later use explosives to break the rock into smaller pieces. So drilling is like a key step to make sure we can get the gold out in the best way possible. When we make holes in the ground to find gold, we need to think about how deep these holes should be. This depends on the kind of rocks and how we want the rocks to break. If we need the rocks to break a lot, we make deeper holes. These deep holes help when we use explosives to break the rocks and get the gold. But making holes isn't just about explosives. It's also like taking samples of the rocks. These samples, called core samples, are like pieces of rock taken from the holes. They're important because they help scientists understand what the rocks are made of and where the gold is. So drilling in gold mining is a careful and flexible step that helps both in getting the gold out practically and understanding the rocks scientifically. In gold mining, drilling is not just about exploring, it's crucial for getting the gold out. After making careful holes in the hard rock around where the gold is, the next big step is to use explosives strategically. This is a super important phase because it's all about breaking the tough rock to get to the gold. Choosing the right explosives like dynamite is a big decision. It depends on what kind of rock it is and how much we want it to break. Once the holes are made, we put in just the right amount of explosives to break the rock into pieces without causing extra damage. This whole process is a key part of taking the gold out of the ground. When we set off the explosives in the holes, it's like a carefully planned burst of energy. This controlled explosion creates a powerful shock wave that moves through the rock, breaking it along specific lines we decided earlier. The result is that the hard rock shatters into smaller, more manageable pieces. This broken rock now holds the valuable gold. It becomes loose and is ready to be taken out. The whole process of drilling and using explosives in a careful sequence ensures that we can efficiently get the gold ready for the next steps in the mining process. It's a crucial part of making the mining operation successful. After breaking the hard rock containing gold with explosives, the next important steps are moving and processing the broken rock. This loosened rock needs to be brought up to the surface for more work. Different methods, like underground conveyors or skip systems, are used based on how the mine is set up. Once above ground, the broken rock goes to a processing plant. Here it goes through different stages, starting with crushing and grinding to get the valuable gold out from the rock. In industries, crushing is a vital step used in various operations such as mining, mineral processing, construction, and recycling. The main goal of crushing is to make the raw materials smaller so they can be used or processed more easily. The process begins with the raw gold or being fed into a primary crusher. Common types of crushers used for primary crushing in gold ore processing include jaw crushers, gyratory crushers, and impact crushers. The primary crusher applies mechanical force to break down the larger chunks of gold-bearing ore into smaller, more manageable pieces. This reduction in particle size is crucial for the liberation of gold particles from the host rock. Once the gold ore is crushed, it's turned into a fine powder through grinding. This powder is then separated using methods like shaking tables, which look at how heavy the gold is. Another method called froth flotation separates gold by making it stick to bubbles. Cyanidation is a process where the crushed material mixes with a solution that has cyanide. This makes a gold cyanide mix, which can be turned into pure gold. Some other ways, like carbon in leach, CIL, or carbon in pulp, CIP, use something called activated carbon to get the gold. Smelting, which is like heating things up a lot, helps separate gold from other stuff in the crushed material. Finally, refining, which uses methods like electricity or chemicals, removes anything left, giving us pure gold. The way we choose depends on what the gold in the rock is like and how pure we want it to be in the end. Making a gold brick involves several steps in the refining process. After the initial extraction and processing of gold ore, the remaining gold is often in the form of a powder or concentrate. To create a solid gold brick, the gold is subjected to smelting, a process where it is heated to high temperatures to separate impurities and shape the gold into a molten state. This molten gold is then poured into molds and allowed to cool, resulting in the formation of a solid gold brick or bar. This final product represents a purified and standardized form of gold, ready for various applications such as investment or industrial use. Gold is used in lots of ways because it's special. People use it to make beautiful jewelry that lasts a long time. It's also like a safe way to keep money because it doesn't lose its value easily. In phones and computers, gold helps them work because it's really good at carrying electricity. Doctors even use tiny bits of gold to help with tests and medicine. Gold is also in some parts of spacecraft windows to keep them safe, and in dental work to make strong teeth. It's even in some really cool art and things like fancy watches. So gold isn't just for looking pretty, it helps in many different things all around us.